Welcome everybody to another physics class. In today's lesson, we're going to be discussing uniform circular motion. Before we get started, I'd like to emphasize that this is not a replacement of anything else, but this is simply to enhance and clarify your understanding of the material. Before we get started, let's go ahead and tackle some of the vocabulary. The word centry on its own means center, and the word pedal on its own means seeking or moving toward. So when you combine the two as centripetal, that means that it is something that is center seeking, seeking the center, or moving towards the center. So when you get the word of centripetal force, it is a force that is seeking the center and moving towards the center. It's also important to recognize that centripetal force is a net force. With the word centripetal acceleration, again, you get the same centripetal in there. Therefore, it is an acceleration that is seeking the center or moving towards the center. And it's also important to note that the direction of force and acceleration are always the same. And this is still true in a circular motion. We also have tangential velocity, which is the linear speed of an object moving along in a circle path. This is not moving towards the center. Now, you may have heard of the saying that a speaker or someone went off on a tangent, and this is what they refer to. Of course, you know tangent from geometry when it's a straight line off a circle, but if the saying of speaker went off on a tangent could be related to this issue and also could help us clarify with circular motion. The topic and the focus is what should be the center of that circle, the discussion. However, at some point, the speaker decided to go off on a tangent and completely ended up somewhere else on a different topic. So this is what they mean by a speaker or someone went off on a tangent, is you started somewhere specific and you were going around that topic, and all of a sudden something happened and you went off on a tangent and you ended up somewhere else. A better example of this could be what you're doing right now, and you're watching a YouTube video, and how many times have you been paying attention to the actual video and focusing on it, which is the topic, and then you kind of think about something else and you start looking at the playlist and you look at the recommended playlist next to the suggested videos, and then you start clicking on it and you end up totally somewhere else than when you first started. And it's important to think about that example because the final moment that you stop paying focus is the moment that you started to go off on a tangent and ended up in that same direction that you were looking at. So this comes into handy with circular motion as well, because if we say that where the line is, that top green dot, if at that point the centripetal force was no longer being applied and there was no more force being applied, if it stopped at that point, by that I mean if the force stopped at that point, then that object would go off on a tangent in that line that you see in that direction. All right, centripetal acceleration. Again, remember that centripetal means center seeking or towards the center, moving towards the center. So if we're talking about acceleration, those are vectors that are going towards the center. And we have different points labeled A, B, C, and D. And depending on where that object is, we could say at that point where it's headed towards. So if the object is at point A, the centripetal acceleration is always towards the center, but you could also say that it is towards the south. If we're talking about point D, it is still moving towards the center as far as centripetal acceleration is concerned, but now it's moving towards east. And it changes based on where the object is. So likewise, at point B, the centripetal acceleration for the object is still towards the center, or you could say that it's moving towards west. So centripetal acceleration in our Formula chart is equation number 12, and it is AC is equal to V squared divided by R. Of course, the C is the subscript, and that is for centripetal acceleration, and any kind of acceleration is in meters per second squared. The velocity is our tangential speed or tangent velocity, and any kind of velocity is always in meters per second. And finally, we have our R, which is the radius. And the radius, just like any other measurement of length, should be in meters. A key thing to remember is that centripetal acceleration always points towards the center of the circle. Okay, moving on to centripetal force. The image looks the same. Again, we said that the force and acceleration, the direction of those two vectors, is always in the same direction. So with centripetal force, the equation in our formula chart is equation number 13, and that is Fc is equal to m times v squared divided by r. Of course, Fc stands for centripetal force, and any kind of force should always be in newtons. V is still our tangent speed or tangent velocity in meters per second, and r is still our radius in meters. Centripetal force can be put into the equation of mass times centripetal acceleration, because if you remember from the previous slide, centripetal acceleration was v squared divided by r. So you may be given centripetal acceleration in the problem, and if you have the mass, you can multiply the two and you can get your centripetal force. Moving on to tangential velocity or tangential speed, you now have what's called a counterclockwise rotation and a clockwise rotation, and it is important to notice the difference and the similarities between the two. The similarities is that regardless of which way it's rotating, the direction of the force, even though there's no force vector labeled here, the direction of the force and the acceleration are always the same, which is always towards the center. There is no difference in that sense. So centripetal force and centripetal acceleration for both of these circles, regardless of their rotation, is always pointing towards the center. What does change, however, is their tangent velocity vectors. So if we're looking at the one on the right with the blue, and if we're looking at point D in the right, the tangential velocity is towards the south or bottom of the page. At point C for the one on the right, tangential velocity is towards the east or to the right. At point B, tangential velocity could be said that it's going towards the north. Likewise, if we switch over to the left, if we compare the points B from the left side to the right side, on the clockwise rotation with the red vectors at point B, tangential velocity is now pointed towards south. Whereas point C, the tangential velocity vector, is headed towards the west. And tangential velocity at point D is headed north on the clockwise rotation. So again, centripetal force and centripetal acceleration are always the same, always towards the center. However, the tangent velocity changes depending on the rotation of the circle. The velocity in uniform circular motion, with our equation being equation number 11, is Vt is equal to 2 pi r divided by capital T. Now, the first T that you see next to the V, that's a subscript to tell you that it's referring to the tangential velocity. The second T that you see, the capital T, that is the period of a revolution. And the R, of course, is our radius, and that should be in meters. All right, so let's not confuse our T's. The capital T stands for period. I know it doesn't make any sense, but the capital T stands for period. And it's the amount of time it takes for one full rotation or revolution, which is a fancy word for saying circle, of an object. So it's the amount of time that it takes to complete one full rotation or one revolution of an object. And this was going to be in seconds. In order to solve for period, there's two different methods. You can divide the number of seconds by the number of revolutions, or you can use equation number 42 in your formula chart, which is T is equal to 1 over F, where F is the frequency and the units of frequency is in hertz. Let's not forget that the lowercase t stands for time, and that should always be in seconds. And finally, the subscript of t next to v for Vt is tangential velocity or tangential speed, and that should be meters per second. So again, don't confuse capital T, which is period, with lowercase t, even though both of those units are in seconds. One of the most common mistake is when students start using these equations and they see the capital T for period, they simply take the number of seconds and put it there. So again, remember, there's two different ways to find period. The first one is divide seconds by revolutions if you have those two values, Or if they don't give you that value, chances are they've given you the frequency. So you could do 1 over the frequency. All right, so seeing the relationship between period and frequency. So remember, the capital T stands for period, and that's the time that it takes for one full rotation or revolution of an object. So again, this is where we do the seconds divided by the number of revolutions. With frequency, it's the number of rotations or revolutions per unit of time, which really means per 1 second, measured in hertz. So the equation is T is equal to 1 over F. And if you're solving for frequency, it becomes 1 over T. Let's say that you're given a frequency of 0.5 hertz and you're trying to solve for the period or capital T. Use the equation 42. Capital T or period is equal to 1 over F. So you do 1 over 0.5 hertz and you get 2 seconds. What this means is that it takes us 2 seconds to do one full rotation. That's our period. However, for each 1 second, we do half a rotation. That's our frequency. So the period in this case is 2 seconds because it takes 2 seconds to complete one full revolution or circle. And the frequency is that in 1 second, you do half of a rotation. And that's where you get the 0.5 hertz. All right, let's go ahead and do some sample problems. And the problems that I'm going to go ahead and show you guys are going to be the multi-step and the more difficult problems. These are not the straightforward, simple ones, as at this point, I expect you guys to be able to plug in the numbers for their variables and be able to solve them. So let's just say that there's a problem for centrifugal acceleration. If you're given velocity and radius, you should be able to simply plug that in, v squared divided by r, and get your answer. So I'm not going to be doing the easy ones. Instead, I'm going to be showing you some of the more complex or multi-step ones, as these might be something that you may be having difficulty with. Remember to never jump to an equation, despite which specific variable the question may be asking for. For example, you may be solving for tangent velocity or radius, but you can find those values from either equations 11, 12, or 13. So you should always write your knowns and unknowns and narrow down the equations that you will need to use. Now, it could be one equation or it could be multiple equations. And sometimes you may have to use 2 or more equations in order to solve a problem. So let's go and get started. Problem number 1. An object on the end of a 4-meter long string completes 8 circles in 4 seconds. What is the velocity of the rubber stopper? So, one key thing is that the length of the string is your radius. Don't divide this. That's a big common mistake that is made often year after year. However long your string is, that is your radius. Because if you imagine that you're holding that string, and from your hand would be considered the center of the circle, and the end of that string is where the object is, and as you're making a circular motion, it is going around, so the radius is that 4 meters. And since it's moving in a circular motion, the velocity that it's referring to is the tangential velocity. So we're solving for our tangent velocity, which is our unknown in meters per second. The radius is 4 meters, and our time is 8 seconds. Now, the number of circles or the revolutions that we had was 16. It's important to note that lowercase t and capital T are 2 different variables. Lowercase t is your time, 8 seconds, and capital T is your period, which is what we need to solve for. We can find t, the period, by dividing the seconds by number of revolutions or circles. In this case, we had 8 seconds divided by 16 revolutions, which is equal to 0.5 seconds or half a second. So our period it takes us half a second to do one full circle or one full rotation. And now that we have period or capital T, we can now use equation 11 to proceed and find our answer. Equation 11 is tangent velocity is equal to 2 pi r divided by the period. We go ahead and substitute our values. The 2 pi is still the same there. The radius was 4, so it's 2 pi times 4 divided by the 0.5, which is the half a second that it takes to do one circle. When we punch it in the calculator, our tangent velocity for this problem is 50.27 meters per second. Now, this is a perfect example of a problem in which you needed to take one step first before you can solve the problem. In this case, we had to solve for period first before we could go ahead and solve for our tangent velocity. As I've pointed out, a common mistake is many students will take that 8 seconds and punch it at the very bottom where that T is. That capital T is your period, and you can't simply just take your seconds and put it there. You have to solve for actual period. Remember that there's two ways. In this one, we used the first method, which was the number of seconds divided by the number of circles. So pay close attention to what you're doing, and you should avoid these little tiny mistakes. Problem number 2. A bumper car has a mass of 90 kilograms. A force of 450 newtons keeps the bumper car moving in a circular path with a radius of 8 meters. Calculate the speed at which the bumper car travels in the circular path. Okay, so some of you may be overconfident, or you may be in a habit and say, oh, it's asking for speed, therefore it's got to be equation 11. Remember that we do not jump to any equations because we don't know which one we're going to be using. Instead, rely on writing your unknowns and knowns and then go from there. So we are solving for tangent velocity. That's our unknown, with units being meters per second. The car had a mass of 90 kilograms. The centripetal force, even though they don't mention it, they just say a force of 450 newtons. It is a centripetal force, is 450 newtons. And the radius of this circular path is 8 meters. So when you look at our equations, we have tangent velocity, we have mass, centripetal force, and r as our 4 variables, and that fits into equation number 13. Even though number 13 says that it is for centripetal force, you can go ahead and solve for any of the other variables in it. And that's what we're doing today. So equation number 13 is centripetal force, Fc, is equal to mass times velocity squared divided by r. So your first step is to get rid of the r by multiplying it on both sides, and you get r times centripetal force is equal to mass times velocity squared. Divide velocity squared by mass to get rid of the m, which you do to one side, do to the other. So you get velocity squared is equal to radius times centripetal force divided by mass. And finally, one big step that you don't want to forget is to take the square root of the v, because right now it's v squared. Take the square root and you get tangent velocity is equal to the square root of the radius times the centripetal force divided by the mass. And you can go ahead and substitute your values from there. Our radius was 8, our centripetal force was 450, and our mass was 90. You want to make sure that the 8 and 450 are multiplied first, and then you divide that by 90, which is equal to 40, and ultimately you want to take the square root of 40. So the tangential velocity is 6.32 meters per second in this problem. So this is a perfect example of never jumping to an equation and never selecting one just because you think it's asking for a certain variable. Moving on to problem number 3. A 3.0 times 10 to the third kilogram car travels with an acceleration of 40 meters per second squared around a circular curve with a velocity of 15 meters per second. What is the radius of this curve? And this is a type of problem that, there's no specific equation that says this is how you solve for r or the radius. Instead, you have to use either equation 11, 12, or 13. So this is why I stress that you write your variables and select your equation from there. So radius is unknown, and that's in meters. Our mass is 3.0 times 10 to the third kilograms. Our tangent velocity is 15 meters per second, and our centripetal acceleration is 40 meters per second squared. Now, as you write every single variable down and you compare it to your equations, not every variable may need to be used. In this case, mass is excessive, and the other three can be used in equation 12. So equation 12 is centripetal acceleration, AC, is equal to v squared divided by r. And we go ahead and substitute our values. Centripetal acceleration was 40, and our velocity was 15, so it's 40 is equal to 15 squared divided by r. Since we want to solve for r, we have to multiply by r on both sides, and it cancels out on the right. So we get 40 times r is equal to 225, the 225 being the 15 squared. Ultimately, you want to solve for r or isolate for r. So you divide by 40 on both sides. Cancels out on the left-hand side, and you get 225 divided by 40 on the right-hand side, which is the radius, is equal to 5.63 meters. So again, not every variable may need to be used. Just take your time identifying everything that you have and compare it to the equations you have and go from there. Problem number 4. A car travels around an 80-meter radius circular path at a constant velocity of 90 meters per second. The frictional force that the car experiences is 25,000 newtons. What is the mass of the car? So now some of you might be seeing that frictional force, you may be a little bummed out about it. One, we're never really done with anything because we always build upon the previous material. 2, remember that frictional force is what provides the centripetal force required for a car to travel in a circular motion. So the centripetal force is a net force, and in this case, for this problem, that net force is provided by the frictional force. So your frictional force is equal to your centripetal force. Let's go ahead and write our knowns and unknowns. We're solving for mass, which is unknown variable for us, and the unit is in kilograms. Centripetal force is 25,000 newtons. Tangent velocity is 90 meters per second, and our radius is 80 meters. So we have those 4 variables, and based on those 4, we can use equation number 12, which is centripetal force is equal to mass times tangent velocity squared divided by the r. Now, it's just the v that is squared on its own. Nothing else. It's just the v that is being squared. We go ahead and substitute our values. Centripetal force was 25,000. Mass is our unknown, so we're going to go ahead and write m as it is. The velocity was 90, and that's the one that gets squared, so 90 squared. And that is divided by our radius, which is our 80. So in order to solve for mass, the first thing we need to do is multiply by 80 on both sides. It cancels out on the right-hand side, and we get 80 times 25,000 on the left-hand side is equal to mass times 90 squared. We're going to go ahead and rewrite that equation. 80 times 25,000 is equal to 2 million, and 90 squared is 8,100 times m. Again, we're solving for m, so we're going to go ahead and divide by 8,100 on the right-hand side. Those cancel out. And we're going to divide 2 million on the left-hand side by 8,100 as well. And we get our mass as 246.91 kilograms. So these are a couple of problems in which they're asking for different variables. They're not just straightforward saying what is a centripetal force, what is a centripetal acceleration. If those are the type of problems, those are very easy to plug in. These are different questions that uses the same variables, but they're asking you to find something else, a little different. So I hope that these problems were helpful. Now, one other thing to review on is how to find the arc length. And it is important to understand that this method only works if you're given the angle in degrees and not radians. Of course, in physics, we're always going to give it to you in degrees, so you don't have to worry about it. But just a little side note. So in order to find the arc length, which is that little piece that the arc length is written on that circle, the formula is 2 pi r times the angle theta divided by 360. So if we are given a problem and the radius is 10 and the angle is 135 degrees, then we are going to go ahead and substitute those values. So it was 2 pi r times the angle divided by 360. So when we substitute it, it is 2 pi, the radius being 10, 2 pi 10 times the angle theta, 135 divided by 360. Just rewrite each step, and you get essentially 2 times 3.14 times 10 multiplied by the 135 divided by 360. On the left-hand side, 2 times 3.14 times 10 is equal to 62.8. And that's still being multiplied by 135 divided by 360, which when you punch it in the calculator is the equivalent of 0.375. So we take the 62.8 times 0.375, multiply them together, and we get the arc length as 23.55 meters. Okay, that wraps it up as the overview for uniform circular motion. I hope this video has been helpful. Have a wonderful day.